Hi, RDBury here. Welcome to another episode in my series on strange arithmetic. This time what we're going to do is cubic bases. In other words, the irrational bases that are the solutions to cubic equations. We've already done some irrational bases that are solutions to quadratic equations. And last time we talked a bit about PV numbers. In other words, well, you can watch the episode for that. But basically, to get the bases that work, what we want to do is look at PV numbers. And it turns out the smallest quadratic PV number, which is in I guess you could say is the simplest PV number, is phi, which turns out to be the first episode we did. The next episode was about quadratic PV numbers, and although I didn't mention it at the time. And so now the procedure is we look at all PV numbers of a given degree within a certain range, and there will be a finite number of them, and we'll look at the what happens when you use those as a base. So this episode, I'm looking at the cubic PV numbers between 1 and 3. Turns out there are 4 between 1 and 2, and 16 between 2 and 3. I'm going to do the ones between 1 and 2 in more detail and just sort of briefly cover the other ones. The So we're just going to cover the ones between 2 and 3 quickly and do more detail on the ones between 1 and 2. So let's get started with that. I've started out with the so-called Tribonacci constant, and the magic formula for that is here. It's very similar to the Fibonacci constant, which is also called phi. And the arithmetic in this base is very similar, but what you get here is that instead of this kind of symmetric um, placement of the digits around the decimal point, they expand to the right of the decimal point about twice as fast as they do to the left, and you don't get the nice simple run length patterns that we saw earlier in the quadratic case. So that whole system is out the window. Apparently, it doesn't really hold for cubic bases, or if there is a version that holds, it is very much more complicated than it is for the cubic bases, or than it is for the quadratic bases. And that happens sometimes. Sometimes you see a pattern that works for that starts to work, and then it just sort of falls apart, and there's nothing you can really do about it. Now this number is very close to 2, so on the left here you see numbers that look very much like accounting base 2. The difference is if you have 3 ones in a row, you can do a carry. So there's no you don't get 3 ones in a row anywhere in these expansions. But other than that, in terms of the distributions of ones and zeros, notice here the zeros are kind of implied here. I've hidden them so to make the ones stand out a little bit better. They are there in the cells, though. So the distribution of ones and zeros is about the same as it is for binary. That will get less and less true as we go down our list. I'm starting right now with the largest base between between or that's less than 2. So that's what it looks like, and let's continue on to the next one. So the first surprise, I guess, is that when you get to cubic, um, the length of the expansion to the right of the decimal point, place, it continues much faster than it does on for quadratic ones, which isn't too much of a surprise, because for linear bases, which would just be numbers or whole numbers greater than 1, there isn't anything over here at all. It's just you're just going up to the decimal place and decimal point and stopping. For quadratic, it goes about the same distance or the same length to the right, and so for cubic, you would expect that it would be about twice the distance. That happens sometimes, and when that happens is when the last digit here is, or the last coefficient here is plus or minus 1. When it's a larger value in size, then these expansions to the right get large or grow even faster. So anyway, enough of that, I think. Now I'm going to go to this one, which is similar. This one, the magic formula is almost the same, except that I've replaced one of the negative ones here with a 0. And that's corresponding to a base which is similar to the Tribonacci sequence, only you add the previous number and the number, then you skip one and add that number. So that's also similar to the Fibonacci sequence in the way it's defined, but so you could call it a generalization, but it's a bit different than the other generalization. So and this one, we start getting some interesting things happen here. First of all, in all the bases we've looked at so far, if you add the digits on the expansion, you get a number which is less than the actual number. Here we get something where that doesn't hold, because you get the sum of the digits here is 3, but this is for the expansion for 2. And that's something that starts happening with the cubic bases. It doesn't happen with quadratics at all. And perhaps not coincidentally here, another thing that happens is that the length of the expansions on the right don't necessarily increase. Here we have an example where the length of the expansion on the right is 10, but on the next one it's only 7. So this can go up and down depending on the number. The trend will always be to increase, but it doesn't have to all the time. And you can see that occurring more than once in this particular base. Here it happens again. Here you just have this oddball, which seems to be a carryover from over here. Another one where it decreases twice in a row, apparently. Now I've done all the numbers here up to 100, so I'm starting to run out of data here. But you can see it just sort of happens a lot, kind of in a random pattern. So you can say something about the trend, that it will be expanding about twice as fast on the right as on the left, but it doesn't necessarily expand all the time. Sometimes it contracts, sometimes it expands. It just gives you this kind of odd and perhaps interesting exceptions there. So I think that's about all I can say for that. And so the next one I'm going to do is the so-called plastic number. we talked about this a little bit before. Now, one thing, the magic formula here is that you replace the first one of the ones in the Tribonacci constant with a 0 here. And this turns out to be very close to, I think it's about 1.3 approximately. But it is the only, as far as I know, it's the only PV number that's less than the square root of 2. And that's of any degree. It's the smallest PV number of all. So what happens is that since this is less than the square root of 2, the expansion for 2 turns out to start in the hundreds place here. So that's the only case where you see the 1 here, and the next, and for the 2 you don't start here but over the next digit over. And it is not that much smaller than the square root of 2, so you have to go a long way over to the right to get the next digit. The other thing you'll notice is that this is such a small number, you need a lot of zeros after each one, and in fact you need at least 4. This is one where you have the minimum possible. If you have a 1 0 0 0 1, then it turns out you can do a carry, and so that combination isn't allowed. Now this one, the expansion, as this expands to the left so quickly because the base is so small, it expands to the right about twice as fast, and that gets very large even more rapidly than the others. One thing you kind of notice about this is that if the information kind of stays constant. So at a base like this, where you don't really have a lot of information in each digit, you kind of need to have a lot of digits to make up for that and get the same amount of information in the expansion. So this is kind of an interesting one. It's kind of a pain to do these computations because they turn out so long each time. It's a lot easier to do a base like this because you can see how much less of a expansion you have to do. But this one, it's like you have to do twice as much work to get the same result here. So that is to me, this is one of the most interesting, but it's also, like I said, the one of the most difficult to actually deal with. So anyway, I think that's all I have to say about the ones between. No, it isn't. Okay, I still have one more to cover. Sorry. Between 1 and -1, and that's the plastic number squared. I said last time the power of a PV number is always going to be another PV number. This is less than the square root of 2, so its square is going to be less than 2. And so it's going to be included on this list, and it turns out it's included right here. Now this one, the magic formula looks like this. It's got negative numbers and positive numbers in there. There's no rule that says that can't happen. And the rule here is a bit more complicated than the other ones. Basically says it says if you have 2 1s in a row, then it must be followed by 2 zeros. And again, the the lengths on the right here kind of increase and decrease. They will, again, on average increase, but they don't, it's not consistent with that. So again, another kind of interesting pattern here. It's also a little bit difficult to work with because the rule for the digits is a little bit more complicated than the others. They do get more and more complicated the higher you go, though. So for the rest of these, I'm just going to do in order of size, because I think we've seen a lot of the surprises so far. There are still going to be some surprises, but let's continue on just to see what else might happen. This is going to be the first number greater than 2. I've put the zeros back in because now we have more than zeros and ones to worry about. So this is almost like binary, except you do get the occasional 2 in the expansion. And the rule for that, you can read off from here. You must have at least 2 zeros, and then if there's something other than 0 after those 2 zeros, it must be a 1. And if there's something after that 1, then it must be another. It must be in fact 0. So you can't have 2 0 0 1 1 or anything that is bigger than that in dictionary order. And what I've done here, this is kind of a way of doing those carries. If I have a 3, then I can add this number, add this string to it and use that to do a carry. If I have a 2 and a 1, then I can add this to do a carry. And you can use something like this with a lot of these bases to deal with these kind of complicated digit rules. It isn't always practical in all cases, because these digit rules can turn out to be as long as you want in for cubic bases. We shall see one later that gets longer than this one even. So this is a more complicated rule here, but it does seem to behave fairly well in terms of its other properties. Again, notice that the expansions on the right are not increasing all the time. Let's see. Let's go on to the next one. This is similar to one of the ones we've done earlier, but it's again slightly bigger than 2. And again, I've put my carry rules here in this form. In this case, again, you notice you get this this increase and decrease in the lengths on the right, and also the sum of the digits here is 5, which is bigger than 3, which is the original number. So again, some things that are similar to what we've seen before, just a little bit different case. Now this one, wow, okay, this one turns out to be very interesting because as soon as you get to 3, the expansions don't terminate. You get this number, you get this number up to here, and then after this point, the 4th digit, it just alternates 0 1 0 1. So you've got like a repeating decimal, even though it's not a fraction. It's just the number 3. And in this case, you get this repeating decimal, at least as near as I can tell. I've done this out to 100. But you get this repeating decimal up to for every whole number here, except for just 1 and 2, in which case it's just the number itself. So that's that's kind of a surprise. You wouldn't expect that to happen. And I think the first time I tried this and I got this repeating decimal, I was thinking, wow, what the heck is going on with this? Because it just sort of surprised me that you could have this kind of repeating pattern here instead of just a terminating decimal, even though it's basically in the same category as the other ones we've done, and it does. It's not a random pattern here, but it is a it is a non-terminating pattern, and this is one thing that I'm not. I don't think that was covered in the original paper on base phi. It didn't really cover or didn't really prove that you wouldn't get this this kind of phenomenon where the expansion just doesn't end, even if you're starting out with a whole number. Even if you're representing a whole number. It's actually not hard to prove that, but it's something that is a theorem and not just an obvious fact. So that's an interesting surprise. And so apparently there's numbers or bases where once you get up to, once you have to start expanding, then they kind of just keep on going forever instead of stopping like you might expect. This one I think behaves a little bit more normally. It does end in a 2 over here, so the lengths of these expansions to the right are getting longer much faster than the other ones. But I don't think there's any that actually continue on forever. You can see that they go on for a very long time. But in terms of going on infinitely long, that doesn't seem to happen with this one. It's probably not hard to prove that. It's probably I'm guessing it could be done, but it would not be. It would be a bit tedious, I think, to do that. So I haven't really done that. And there's just so many that, I mean, once you've gotten to 100 and you haven't seen any repeats yet, I think it's kind of obvious that there won't be. But proving it is probably not that hard, but I haven't done it. So anyway. All right, so next one is another one where we have possibly repeating decimals for whole numbers. In this case, it doesn't seem to follow a regular pattern. In the previous one, it just, once you got up to above 2, it just started, it just was always repeating no matter what. This one, you get 3 and 4 repeating, and then 5 doesn't repeat. And then the next one that repeats is up here at 28, and then 28 through 46 repeat, and then you get a 47 stops. So this one is, you seem to get this sort of a random pattern of stopping and not stopping. So that's another kind of interesting thing that's going on. Now I tried to graph that, but it wasn't really very enlightening. But again, it's another kind of surprise. I mean, so far we've had it either stops all the time or it continues nearly all the time. And this one, it just seems to stop and start, in chunks. But it's hard to tell what it will do. I mean, if once you get beyond a certain point, it's hard to tell what it's going to do. if I picked, say, a random, like a large enough number, say 1,000, I would have no idea whether that stops or starts. So it seems to be more or less unpredictable unless you actually carry out the computation. Now here, this is all I've done here is put in the actual value of the root and then computed the other roots as they turned out to be complex numbers, because I was doing some experiments with that. This one here is similar to some of the other ones in some ways, and not some of the other ones in other ways. So the magic formula is here. Again, it ends with a 2, so the numbers on the right expand very quickly, but it turns out they don't ever repeat, it looks like. It's hard to, like I said, it's hard to be sure, but at least for the first 100, they don't. Okay, and again, another one that ends with a 2, so this one expands very quickly, but it also has another some occasional infinite expansions. In this case, it's the period of these decimals is 5. So it's not only does it expand periodically, but it's not even a simple expansion. So that's a little odd. And when it does repeat like this, I mean, you can call the length of time before it actually enters this repeating cycle the length. And again, the length does increase rapidly. I mean, you could say this is infinite length, but if you remove all these repeating parts, then you get the actual length, you could say. So the actual length still does increase rapidly. The next one is here. This one, again, we get a period of 5 repeated pattern. I don't know if this. Yeah, we've got some here still down here that are finite. They are very long, but they do stop. So it's another case where whether it repeats or not is kind of hard to determine without actually carrying out the computation. So there's the formula for that. This one, turns out to be rather well behaved, and it turns out if the numbers here the numbers are 2, 1, 1, if that's a decreasing sequence, or at least if the negatives form a decreasing sequence, you get a fairly well behaved base here. Now, one thing that kind of surprised me is that it does still happen occasionally that you get a decrease in the length of the expansion to the right. See, it happens right here. I don't think that happens ever again up to 100. So that seems to be a rare phenomenon. It does happen occasionally, though, and that did surprise me, because supposedly this is supposed to be a more well-behaved base than the other ones. Let's continue on. This is another one that ends with a 2, so it expands rapidly on the right, and again you get this. It seems to always be finite, but it does sometimes decrease in length. And I think we're almost done here. Again, this is pretty much in the same lines we've seen before, so I won't go into this too much. This one is another one that decreases to 2, 1. So this is, again, fairly well behaved. None of that stuff where it decreases in length at all. So it's hard to tell whether that's just coincidence. It hasn't done it up to now, but it might do it in the future. I don't know. Another one that ends with a 2. And this one, this has a very complicated rule here. I won't even bother trying to explain it here. And this, when it gets this complicated, you have to kind of go to extraordinary lengths to figure this out. So what I've done here is, so I think what I had to do here is, and I might have done this on one of the other ones, but you really have to compute the exact value. You have to put the value of the root. You have to compute the value of the root, and then evaluate what you've got so far, and then actually figure out whether it's +1 or -1. I mean, theoretically, you wouldn't have to do it, but you don't. There's not that much time unless you try to do this by computer. So the normal carry and borrow rules get so complicated that basically you need a computer to work them out. And again, since it ends with a 2, the numbers on the right tend to or the expansions on the right tend to increase fairly rapidly. And I think there aren't any repeating patterns here, but they do get long rather quickly. Let's see, I think there's 2 more to go here. No, 3 more. Okay. This one, this one is similar to the square of the phi base, in that integers or whole numbers always terminate, but there are other ones that where you start out with something just positive and negative. Once you start to borrow, I should say, once you start to borrow, then you have cases where where you might get infinite expansions on the right. So they aren't shown here, but it can happen. Otherwise, it's fairly well behaved, as you can see. Let's see. This one, I think, is something that's more or less along the lines of what we've seen so far. Just go over to the left here to show what that is. And finally, we have the one that's closest to 3. This is actually fairly well behaved, except for the expansions on the right grow again rapidly because it ends with a 2, and otherwise it looks fairly normal. So anyway, that is everything. There are let's see, I think there are 36 base or cubic PV numbers between 2 and 3, so I'm not going to do all of those. So I think I'm going to wrap it up there in terms of irrational bases, and I'm going to next time go over some interesting things you can do with integer bases. So what that means is, instead of changing the base, we're going to change the possible digits you can use. So that leads to some interesting phenomenon, and I hope you will find that interesting and watch that. Until then, Bye.